So in this discussion session, what we will discuss today would be covariant laws in special relativity. The energy momentum relation which we have seen the examples of before, and the ways to derive the correct special relativistic kinetic energy, where we saw that higher order momentum terms are allowed from special relativity. And then we will use this structure, that correct definition of energy momentum, correct definitions of covariant laws, to apply to quantum mechanics, and we will see what kind of covariant quantum equations do we land up with. Okay, so let's get going and resume our discussion from the previous discussion session which we had. Okay, so in the previous discussion session, we realized that there can be vectors, there can be covectors, that is rank 0, 1 tensors, and there can be other rank tensor like 2, 0, 0, 2, and those kind of things. The properties of those things being that they transforms with various multiplications of Lorentz transformation matrix lambda. For instance, we know that the vectors transform with multiplication of one transformation matrix lambda. The rank 1, 0 vector transforms like that. Rank 0, 1 tensor transforms like multiplication of a lambda inverse matrix, contraction with lambda inverse matrix, and therefore quantities which are contraction of rank 1, 0 and rank 0, 1, those quantities are invariant. That means they are 0, 0 tensor. They do not transform with any lambda in them. So those would be invariant expressions. They will remain true in all inertial frames because no lambda has to come up when we jump from one frame to another. We saw one example in the sense of a magnitude of a vector, where suppose a vector is given to us, that is a rank 1, 0 tensor, and we want to write down its co-vector version, which will be obtainable from contraction with eta mu nu matrix. So by contraction, as we discussed, the second index of the rank 0, 2 tensor and upper index of rank 1, 0 tensor has to be the same, and they have to be summed over. Nu has to take value 0, 1, 2, 3. Okay, then I get a rank 0, 1 tensor. So ultimately, given a vector, I will convert it into its covector, and then covector and the vector will be contracted together to obtain the rank 0, 0 tensor. And that rank 0, 0 tensor would be invariant across all frames. So if I write down the magnitude in this way of one vector, it will be in prime frames. In unprimed frame, the magnitude will remain same. No lambda matrices are needed to be multiplied to that. So this is reminiscent of what we have previously seen, that the magnitude of a vector in spatial rotations remains the same, and therefore the Newton's law under Galilean transformations were invariant. This time also the same physics or same geometrical argument are being used. However, only difference being the magnitude of the vector is not just the component summed square, but the contraction with upper index and lower index, which will introduce a minus sign somewhere, because remember eta mu nu metric was minus 1, 1, 1 in the diagonals and 0 elsewhere. So it is slightly different than the usual magnitude of spatial vectors, but ultimately magnitude in some sense, and that remains invariant, and that would be a protected quantity across all inertial frames. Now let us get back to the second part of the special relativity, where we have decided that we would write down laws of physics in the way that they remain same across all inertial frame. Okay, so there are two options of doing that. Either I write the laws which are invariant, they do not change at all. For example, speed of light is invariant and a constant. D tau is a invariant but not a constant. So this is one option, that I write down in laws which are invariant. For example, speed of light is c is an invariant statement. It does not change from frame to frame. However, as we saw for Newton's law, when we demanded in Newton's law F was equal to ma, we do not demand under frame transformation F should not change or A should not change. We demanded that the relation should not change. F might change under rotation. Its x component can change, y component can change, and z component can change. Similarly, accelerations x, y, and z components can also change under rotations. However, in Newton's law or Galilean transformation, we had demanded that this relation remains sacred. That relation does not change. Individually, they are allowed to change, but the relation does not change. So this is what we will go through, and these kind of things where things change but the relations does not change are known as covariant laws. So in the similar spirit, I would try to write down acceleration is equal to force, now not in spatial direction but space-time dimensions. So I will define a 4 acceleration. Previously, d2x of 3 space upon dt square was a correct vector acceleration because t for Galilean transformation was invariant, not anymore. So we will define a 4 acceleration. 4 acceleration would be d2x mu upon d tau square. X mu is 4 indices t, x, y, z, and d tau square is an invariant quantity as we have seen. So therefore this quantity transforms like a vector. And on right hand side we should write down some 4 force, that is for not only spatial force, we should know the temporal force in some sense as well. So this would be a covariant law, that would be a vector law in 4 space-time dimension, and therefore it would remain protected if I go across different frame. That means the relation will remain protected. We can see that since force is a 4 vector now in our formalism, it should transform with 1 lambda matrix multiplication. So in the primed frame, another inertial frame, it will be obtained from the previous f through 1 multiplication of lambda matrix. So you see new here, the row and the column of these things are multiplied, and therefore it's a matrix multiplication. Similarly, the acceleration which is appearing on the left hand side, in the primed coordinate it would be d2x primed upon d tau primed square, but since d tau primed is same as d tau, so I can just replace d tau square in the denominator, and that quantity would be the double derivative of dx primed mu with respect to d tau. And I know how x primed mu themselves or dx primed mu themselves transform. They transforms like a vector. So this quantity x primed mu has been written like this, and double derivative has to act on this, which is an invariant derivative because d tau does not change from frame to frame. So therefore, as you can see that the acceleration itself also, since this parameters here lambda mu nu matrix elements dependent upon the velocity upon time of the frame, and inertial frame velocities are supposed to be constant, so they are not supposed to depend on d tau. So d tau would go and hit just the x nu. So I will get the prime coordinate acceleration is obtainable from unprimed frame acceleration through 1 matrix multiplication of lambda. So therefore this and that, force and acceleration, 4 force and 4 acceleration together, if I transform both of them into unprimed frame, they will both earn up a lambda matrix multiplication. And the law which we were looking for was that this relation was supposed to be 0 in the one inertial frame, that is the primed inertial frame. If this has to be 0, then the equality between the transformation, that this is 0, that means this combination should be 0. That will give me the relation over here, that in unprimed coordinates f nu upon m minus d2x nu upon d tau square multiplied with a lambda matrix should be 0. And then we should solve this equation. Now this relation has to be true. This relation has to be true not only for one single Lorentz transformation, but there are infinitely many possible Lorentz transformation. Each velocity along x direction is generating a different transformation matrix. So this relation should be true for all inertial frames. That means all possible lambda mu nu. The only way this equation is going to work out for all possible lambda mu nu, which are infinitely many, is that when these coefficients of all lambda mu nu's individually are 0. That means f nu upon m minus d2x nu upon d tau square should be 0 for all nu. And the relation which we started was that similar kind of relation was true in the primed frame for all mu, meaning all component of this vector was 0 in primed frame. and all components of this vector is still 0 in all unprimed frame. So therefore, the relation between the force and the acceleration has remained protected. So that is one way of writing covariant laws, where you write things in either tensor equations or vector equations. Okay, because if I write in vector equations like this, it has one mu. If I transform, ultimately what will happen, that from prime frame to unprimed frame, if I go, only thing that will happen will be the same kind of equation would be there, and that equation would be contracted with a lambda matrix. And the same logic we will apply, that the relation has to be 0 for all possible lambda. So therefore this relation will become protected quantity across all inertial frame. Similarly, had it been a two index relation, something like some relation like f mu nu minus, let us say something like d dx mu upon d tau dx nu upon d tau. From this also you can see that if this is 0 in one inertial frame, if you go to another inertial frame, this quantity will earn up 2 lambda matrix multiplication, and this quantity will also earn up 2 lambda matrix multiplication, and ultimately you will get a structure like 2 lambdas outside f primed mu nu minus d2 dx primed mu d tau and dx primed nu d tau, and that has to be 0, again arguing that the quantity in the bracket has to be 0 in the prime frame as well. So similar kind of logic with which we can write down physical laws which maintain the same relations can be summarized as they should be either invariant equation or they should be covariant equations. By covariant I mean tensor type equation or vector type equation. Tensor or vector type equations. Tensor meaning matrix multiplication by more than one lambdas, and vector means matrix multiplication with just one lambda. Together we can say that it should be just a tensor equation where rank 1 0 tensor will be vector and all other possibilities will be different rank tensor. So ultimately the covariance means it should be a linear equation with some lambda multiplication, and if that happens, we know that in one frame we can write down the equation that the 4 vector or the tensor in the 4-dimensional space is 0, its all components are 0. The corresponding statement will be, if I have a vector or a tensor whose all components are 0 in one frame, then it is guaranteed that under Lorentz transformation all those components will remain 0 in all inertial frames. So therefore the relation which we have written will be the same in all inertial frames. So that is how we should write down the laws of physics. For example, correct generalization of Newton's law would be this. Let us try to see what more we can learn from invariant kind or covariant kind of equations. So let us see what more invariant kind of laws we can write. Right now we have seen an example of a covariant kind. Let us see if there is an invariant kind of relation or not. For example, we can have a 4 momentum. Previously we had a 3 momentum in the spatial dimension, where momentum was mass times the velocity. Velocity was vector dx upon dt. Now as we know, this is not a vector in space time 4-dimensional, and this is also not a vector in 4 dimension. They were vectors in 3-dimensional space. So correct generalization would be, I should write down the momentum should be 4 vector p mu, and this should be obtainable from 4 velocity dx mu upon d tau with some invariant quantity defined as a mass or the rest mass. As we have seen previously, given a vector, I can find out its covector. It would be contraction with a eta mu nu. So I would obtain p lower mu by just taking eta mu nu summing over nu's, as we have seen previously. So then I have a vector and I have its corresponding covector. And as we have seen, if I take a vector and its corresponding covector, then if I contract them together, I generate an invariant quantity. So that means I contract them, p mu, p lower mu, and there is a summation over mu implied. I have not explicitly written because most of the textbook use something called Einstein's summation convention. Ideally, one should have written down a lambda mu, a p mu and summation over mu. But most of the textbook will say if you see same index in the upper and the lower thing, that means summation is already there. Okay, so p mu up and low, it means that it is p upper mu, p lower mu with a summation over mu is therefore equal to, here also there is a summation over mu, and I write down the two definitions of upper p mu. Upper p mu is this, so I write down m times dx mu upon d tau, and lower p mu, which is eta mu nu times m dx mu d tau. So another m will make it m square eta mu nu times dx nu d tau, and a summation over mu and summation over nu both are there. All right. So now you see that if I do this observation, that I have a double summation mu and nu, dx mu upon d tau is there, eta mu nu is there, dx nu upon d tau is there. So remember we have a structure mu nu eta mu nu dx mu upon d tau and dx nu upon d tau. This quantity is appearing. M square is a constant, so it can go out of the summation. And recall, this eta mu nu dx nu summation over mu nu was nothing but d tau square itself. So ultimately I get a d tau square divided by d tau square in the denominator. So that gives me a minus. So this quantity eta mu nu dx nu was rather minus d tau square. So minus d tau square divided by d tau square will give you -1. And okay, I have written in c is equal to 1 unit, otherwise it would be c square d tau square, here also c square d tau square, so I should get a minus c square. So therefore I will get an answer minus m square c square. Okay, sometimes people write with a dot, here also a dot, here also a dot, such that it is rest mass. It is clear that it is a rest mass. So I do earn up an invariant quantity, which is rest mass square times speed of light square with a minus sign. So this relation, as you see, is an invariant relation. It does not come up with any lambda in it. It is a scalar equation. So therefore, I have an invariant expression that p mu should be minus m square c square. Okay, this relation is an invariant equation, and therefore we can use it in any inertial frame. So if I take 4 vector p mu, whose zeroth component is energy upon c, or the frequency if you like, then the spatial components are just spatial momentum vector, then you can write down that p upper mu, p lower mu contraction, that means summation over mu is implied again, you will get, if you open it up, eta mu nu. So this quantity, this summation here means eta 0 0 p0 p0 plus eta 1 1 p1 p1 plus eta 2 2 p2 p2 and eta 3 3 p3 p3, and no other components are generated because eta mu nu is a diagonal thing, only diagonal elements survive. Eta 0 0 was -1, p0 was e upon c, so you will get a minus e square by c square, and from these quantities, these are just 1 1 1, so px square, py square, pz square, that gives you just the magnitude of the spatial vector. So therefore I will generate a relation which is p mu, which is minus m naught square times c square, as we have seen in the boxed equation, is also equal to minus energy square upon c square plus spatial momentum magnitude square. So therefore the invariant relation which is obtained gives me a relation between energy and momentum. That means energy square upon c square with a minus sign plus momentum magnitude square should better sum up to an invariant quantity. Right hand side is an invariant, therefore left side combination should be invariant. So therefore I have this as an invariant relation, and that invariant relation just tells me that energy of a particle should be momentum square times c square. So energy square of a particle is momentum square times c square plus rest mass square c to the power 4. So this is a total energy of a particle moving in free space with momentum p. Previously in non-relativistic systems, we knew that total energy is just kinetic energy plus potential energy if there is any potential energy. If you remove the potential energy, it is just kinetic energy, which we used to know in non-relativistic physics was p square by 2m. Now, in absence of any potential, that relation is modified to this relation, that energy square is momentum square times c square plus rest mass square times c to the power 4. This is a new relation where even if I have a particle which is not moving with any speed, that means spatial momentum is 0, still its energy will not be 0. In non-relativistic physics, in absence of any potential, if I have a particle which is not moving, its kinetic energy will be 0, and since there is no potential, its total energy will also be 0. Not in special relativity. In special relativity, you would have energy of a particle with 0 momentum, p is equal to 0, is equal to m naught times c square. That is the rest mass energy. This quantity is coming from just the rest mass, not due to any movement. So therefore, special relativity accounts for a rest mass energy of the particle, and therefore if I have to get down the energy contribution in this equation due to its motion, that is the kinetic part, I should better remove the rest mass energy from the total energy. So even if particles were not moving, they contain some energy. So therefore, for moving particles, I should get the correct estimate of their kinetic energy from removing the rest mass energy. So total energy minus rest mass energy should be the kinetic energy. And the total energy I know is square root of p square c square plus m naught square c4. So that quantity is total energy minus rest mass energy is this. Okay. So thus we get a nice relation for kinetic energy. From this, if I assume that its rest mass m naught square c square energy is much larger than p square c square. If its rest mass energy is very large, it is moving with small velocity. That would be the non-relativistic limit, where you are not moving very fast. In that case, you can see that I can pull out m naught square c4. Outside it will come with m naught c square factor, and inside I will get 1 plus p square c square divided by m naught square c4, which one of the c square cancels with the c4, and I will have a square root of 1 plus p square m naught square c square. And from this relation we know, so actually this should be square of this should be much greater than p square c square. So this quantity therefore is a very small quantity. Its momentum is much smaller than its rest mass energy divided by c square. If this quantity is very small, I am getting a structure like 1 plus x, where x is very small, and then we can expand it for small x's. So if I Taylor expand this square root function, I will get 1 plus first order term will be x, second order term will be x square by factorial 2, and so on. So I would have a m naught c square outside, and I have a 1 plus first x, which is m naught square upon half x, rather, because half will come from the square root factor. So that would be 1 plus x by 2 minus x square by 4, or something like that. Sorry, x square by 8 you will get from this, because 1 by 2 factor times 1 by 2 minus 1, and then a 2 factorial. So this kind of expansion you will get, and a minus m naught square c square is coming because we have removed the rest mass energy. Okay, so from there you can see whatever we previously wrote about the kinetic energy comes through. You open this bracket up, m naught c square from here, from this bracket, will cancel with this, and first term will start with a p square by 2 m naught square c square, and outside there is a m naught square upon m naught times c square. So they will cancel each other, and I will get a first term which is p square by 2 m naught. This times that. Then the second order term will be p4 with a minus sign, rather, p4 divided by 8 m naught cube c square, and then there will be higher order terms. So this is the term, remember, which we had introduced in the perturbation theory when we were discussing the correct structure of kinetic term in the time independent perturbation theory approach. So you can see this is not the only term. There are higher order terms which we have not written. So as you increase your velocity, those higher velocity terms will start appearing, and in the full relativistic limit, all the terms in this series expansion should be not ignorably small. So they should be accounted for. So whatever we are doing in Schrodinger equation or Schrodinger mechanics is actually the case where the rest mass wins over the kinetic term handsomely. So that if I totally ignore even this term, I'm at the usual unperturbed Schrodinger equation kind of structure. So the ideas which we have learned, that there are invariant laws, there are covariant laws. Covariant laws are changing component wise, but the relation remains the same. Invariant laws are the things which remain the same across all frames. And we saw some example where F mu nu, the force law, can be written as a 4-vector law. That would be a covariant law, and the momentum relations, or E square is equal to P square C square plus M naught square C4, is a invariant equation that remains same across all frame. However, unfortunately, the Schrodinger equation which we have dealt in the standard quantum mechanics is neither of them, is neither invariant nor covariant. As you can see, Schrodinger equation can be written in this form: I h bar del del t acting on psi should be equal to minus h square by 2m, the Laplacian acting on psi, in absence of any potential, let us say, for the simplistic setting. Now you can see if I do Lorentz transformation, this quantity is not an invariant operator, because if I do, we remember this, these are co-vectors. Del del t, the differential derivative with respect to coordinates, are rank 0, 1 tensor, and the double derivatives are rank 0, 2 tensor. So right now, the way we are writing Schrodinger equation is giving me on the left hand side I h bar del psi upon del t is rank 0, 1 tensor, should be equal to minus h square by 2m Laplacian of psi, that is rank 0, 2 tensor. This equation cannot be true, because rank 0, 1 tensor cannot be equal to rank 0, 2 tensor. This transform with 1 lambda inverse, this transform with 2 lambda inverses. So this equation will not remain the same across all inertial frames. So therefore, Schrodinger equation is not relativistically acceptable equation. It is neither invariant equation nor covariant equation. So we have to drop this equation in favor of some better equation. That we will see what kind of better equation should be used. You can see the problem is coming from the spatial derivatives are appearing twice, and the temporal derivative is appearing only once. And in special relativity, both time and space are just coordinate differentials, coordinate themselves. So therefore, one coordinate should not be given a prestigious position compared to all others. And that is what is happening in Schrodinger equation. Spatial derivatives are being appearing twice, while temporal derivative is only appearing once. So they are not at equal footing. So they will not transform in the same way, and therefore they will not be a covariant or invariant equation. So we have to find a replacement of Schrodinger equation, which is either a vector equation or a scalar equation or some tensor equation. We will see in this course examples of this thing and how to do those. However, as a consequence, when we dump the Schrodinger equation in favor of a better covariant or invariant equation, there will be certain problems or certain concepts which we had developed with Schrodinger mechanism that has to be rechecked and re-evaluated. Okay, so we have used various concepts of Schrodinger equation to learn about predictions of quantum mechanics. Some concepts were built upon using Schrodinger equation. For example, one of the crucial concepts which we had learned from Schrodinger equation was psi mod square was declared to be a probability density. And if this was a probability density, then we knew that from the Schrodinger equation, the following equation can be written, that IH bar del upon del t of the psi mod square is equal to minus h square by 2m, a gradient of a particular quantity. Okay, this you might have done in ordinary quantum mechanics course as well. This can be written as a continuity equation form. Del rho upon del t is divergence of j is equal to 0. So this quantity is rather a divergence. So divergence of j is equal to 0. And we concluded out of it that this is talking about some charge flow and a flux flow across a volume or a surface containing a volume, where the quantity being flowing out and in and is the probability, something declared as a probability density psi mod square, and j was built up was something like this. Okay, and this was given in definition of probability current. So the statement was, from this continuity equation, if a particle is the probability of a particle in a volume, if it is changing, that particle becomes more likely or less likely to be in this volume contained, that change is accounted for the flow of the current across its surface. This is true for any current equation, and this time only the current was given an interpretation of a probability. Now that we know that this equation is not true anymore for special relativistic setting, or is not true for all inertial frames, as to say, then the interpretation or even the establishment of such a equation is under question. So we should worry about what would replace this equation and whether we will be able to adopt this kind of interpretation, that the probability is being lost or changed inside a volume, and that is accounted for by the current crossing the surface containing that volume. Those concepts have to be renegotiated once we change this equation. Okay, fine. So let us go ahead and try to see what kind of equations are candidate equations which can replace the Schrodinger equation. So we want certain operators acting on psi is equal to 0, and we want that operator to be either invariant operator or covariant operator. So do we know such differential operators which change covariantly or invariantly under frame transformation? We do, because we have seen already that this operator, which we have seen previously, minus 1 upon c squared del t square plus Laplacian square, that is an invariant operator equation. So this is an invariant operator, or called a scalar operator, and if that hits psi, and let us say if I put some quantity which is appearing on the right hand side as an invariant quantity, so it could be given some invariant quantity acting on the psi. I am just writing as m, actually should be m square c square for dimensionally consistent structure, but some invariant quantity. Remember, we know certain invariant quantity m square, which was obtainable from p mu, and we also know of speed of light. So all these things can be put together, and dimensionally consistent invariant should be put in. So this looks like an invariant operator equation, where left hand side I have an invariant operator acting on a scalar that should be equal to some invariant quantity times the wave function. Actually, as we will see in the coming classes, this is a particular realistic scenario, and it indeed governs a large set of particles moving relativistically, and this is known as something called a Klein-Gordon equation. And therefore this is at the 0th order, this is a scalar equation. Actually, this can be generalized to higher order spin 1, spin 2, integer spin objects as well, and correspondingly it will become vector equation, tensor equations as well. But the simplest setting which we are writing is a scalar equation, where here this quantity is a scalar. So Klein-Gordon equation, Klein-Gordon operator rather, is an invariant operator. The quantity it acts upon remains the same, because it is an invariant quantity acting on some wave function. Then the same wave function should come up with an invariant object multiplication. So that is a Klein-Gordon equation that we will see in the coming classes, that these are useful operators and we will learn to deal with these operators more systematically. Secondly, we can also have a structure like some invariant operator acts, or let us say covariant equation, where things are not scalars. Previously you saw we are acting the invariant operator on scalar quantity, that psi also does not change. This time probably we can do something better and we can demand that maybe an invariant operator acts on certain quantity which is not necessarily scalar, but then I generate the same quantity back up to an invariant quantity. So just like here, a double derivative structure which we were demanding, I know the Klein-Gordon operator is an invariant operator and gives me something invariant quantity times the wave function back. That invariant quantity is dimensionally m squared c square. If I try to obtain similar kind of thing with first derivative, is there any first derivative operator which is also invariant? And the answer, as we will learn in the course, is yes, potentially I can have a first derivative operator which is invariant. So these are given the name Dirac kind of equations, where something called gamma mu is some matrices. As we will see, this is not a simple equation as that a vector contracted with a del mu. These quantities are rather matrices. These matrices contracting with the rank 0, 1 tensor, acting on again some matrices. So this will be a matrix equation acting on certain matrix, giving you invariant quantity times a matrix. So this, as you can see, it looks like an eigenvalue equation now. A matrix acting on a some wave function has to give me the wave function back, and therefore since the operator is matrix kind of operator, this the wave function should have been a matrix or a column vector itself. Previously it was a scalar over here. Okay, so therefore if I demand existence of some invariant structure, the relativistic approach allows for equations where these wave functions are not just a wave function in the position space, but they have a matrix structure, and therefore it has a more structure than the ordinary quantum mechanics, and this guy give rise to new species with some new quantity. That means scalar over here is again can be written a 1 cross 1 dimensional matrix. Here we have a m cross 1 dimensional matrix. So additional degrees of freedom are generated. A matrix like more entries than one. With one entry, we have this equation, wave function, which we know already. If you have more than one entries, we have to interpret what those more entries mean. And these give rise to spin structure. So how many entries will be there would be known from what spin you are coming up with. And therefore, those spin quantities give you something called a spinor equation. Okay. So we will see that new concepts like spins, which I am writing as a species, the structure will be coming about. And as we have anticipated, once the new equations are operating, we will end up getting new structure of this continuity equation where something else would be appearing in rho, because this equation here where rho was mod psi square and j was this quantity was obtained from the Schrodinger equation. Now we have done away the Schrodinger equation with. So we will have a new definition of probability density, and we will have a new definition of a probability current as well. And then again we have to see the structure which we previously know in the Schrodinger equation approach or non-relativistic approach to exist, that if there is a region, the probability of finding a particle in that region is obtainable from psi mod square integrated over this volume. And if the probability in this volume decays, continuity equation tells me that the probability decay is equal to the flux crossing through the surface. That is the information of the continuity equation. Now we have to see what kind of new continuity equation comes about and what kind of new structure do we earn up if we take up one of these equations to be our guiding equations. Okay, so these will be the structure which we will take from special relativity into the quantum mechanics domain. and the implications of that we will see in the next class onwards. All right, fine. So I stop over here, and in the next class we will start discussing these Klein-Gordon equations and thereafter the Dirac kind of equations. Okay, all right. So I stop here.